Welcome back to another session on meta models. We are probably converging towards the closure of the course. In this particular lecture, I will be talking about what we do after we construct the meta model or the surrogate. If you recall, in the very beginning, I presented a template or a flow chart. You start with the design bounds, then you use a design of experiment to identify the points where you want to run your simulation on the experiment. The responses at those DOE, you construct a meta model. Once you have a meta model, there are multiple things that you can do. One is the design space exploration. You can propagate uncertainties through it to understand what is to perform uncertainty analysis, or you can do an optimization. The discussion in this particular session is going to be on the final segment. After you have constructed your meta model or your surrogate, what is it that you can do? And I have titled this slide as exploring and exploiting a surrogate. Okay. I have titled this as exploring and exploiting a surrogate. So far, we have learned about how to construct a surrogate. There are multiple surrogates that we spoke about. To name a few: polynomial response surface, RBF, radial basis function. And of course, these surrogates are basically regression models that are fitted to responses that are estimated at few design of experiment samples. Again, the number of points that are part of your design of experiments was discussed. How you go about it, it is a chicken and egg problem. So, once we have the meta model, or even before having the meta model, the idea is this F hat that we are talking about is a genuine representation of F. That is our hope. But how good of a representation is again given by the error matrix. That is why we discussed the error matrix part of our surrogate construction. But for the sake of discussion, right now let us say that F is, or rather F hat is more or less equal to F. In this case, we could then use F hat directly to find the optimum point. This is the whole idea of constructing a surrogate, so that you do not have to go to an expensive finite element or a CFD simulation or an experiment again. You could just use the less expensive F hat to do whatever you want to do or achieve. However, just one more step is left. So, you use the F hat to find the optima, which means the combination of the design variables that gives you the minimum y or the F hat value, whatever. And then there is a step of verification. So, you want to use the same optimal design variables, if you would call, and call the expensive function or experiment and find whether the value that is given by F hat and F are the same. Most likely they will not be the same, but at least the difference is it explained by the error metric. That is something that you need to check about. But this is the hope, okay, which we work upon. This is what I told you already. Okay. For this to work well, your F hat should be a very reasonable or a genuine representation of your F. If you are interested in an optimization perspective, this should hold good at least at the optimum, if not in your entire design space. But multiple times we have discussed in this course that oftentimes you do not build meta models to perform optimization, because it will do a function evaluation and pick up an optimal point to which the response value or your thickness could be 12.2 mm, which does not make any sense. It is either 12 or 14. That is a classical example that I had given. So, oftentimes you want to know only the direction in which it increases or the direction in which it decreases, where is my robust zone. So, in that sense, usually our interest is in a general sense across the domain, how does my function vary. So, from that perspective, you want a good representation across your design space. But if you are talking from an optimization perspective, at least around the optima, whether it is a valley or a peak, I want my function to be a very good or the function to be approximated very well around the optima. So, since we are talking about in the context of optimization, a quick recall. We have already discussed this part of the course. The methods can be broadly classified as local and global. The reason why I am saying this local and global was driven by the last point from the previous slide, because when you say that your function approximation around the optimal point at least should be good, it is kind of a exploitation. Okay. This is my point zone of interest and I want to exploit it even further. The other one is exploration. Okay. I want to understand how well my function is varying across the design space, that is exploration. So, usually in optimization, whether it is exploitation or exploration is what the question is, and there is a nice analogy of this in oil wells for instance, okay, because first they explore for the fertile locations. So, that is an exploration. Once they identify this is where the oil is, then it is going to be exploitation, deep drilling. So, that is a basic idea in optimization. When you do, you first want to understand how your design space varies. Once you identify your zone of interest, then you will have to exploit it further. So, if you are coming up with a meta model or an algorithm, it should allow you to do both. You cannot say, okay, here is an approach, well, in a generic sense, you know, if I had a wish list, I come up with an algorithm which lets me do both exploitation as well as exploration. If possible, I want to balance both of them. So, but depending on the application or depending on the specific area that you are looking at, you might only be interested in an exploration or an exploitation. So, we will see. So, the local approach, as I pointed out, is more like exploiters. It gets locked in the local values, but you should be clear about that. Oftentimes we say we bring in a design legacy over the years and we know this is what is a zone of interest. So, it is fine. There might be a global optima elsewhere, but I do not have the resource to go and look for the global optima. Within the local setup, can I get an optima that satisfies my case? And the approaches that are usually used are gradient based, Newton, quasi-Newton, conjugate gradient and other approaches. There are also direct search algorithms which we did not discuss in detail. It could be the pattern search, G1 hooks kind of an approach or a simplex based approach. The other category that we spoke about is the global, which is the explorer. The whole idea, again we did not discuss about this in genetic algorithm or simulated annealing. The whole point is they will explore the different regions and then once they identify basins of attraction or pockets of attraction, then they will put more samples towards that. That is the whole point of genetic algorithm, is finding good offsprings. So, good offspring means basins of attraction. They identify points that will belong to basins of attraction and then they will only mutate with those to generate better samples in those locations. So, it is a both exploration and exploitation kind of a stuff. Okay. So, this is just a recall of the optimization approaches that we. The reason that I am also talking about this is we are going to inherit these ideas when we go ahead while dealing with the meta models. So, the one thing that we want to discuss today is usually I get questions when we talk about meta models, both academia as well as from the industry, but mostly from the industry perspective. What is the thumb rule for selecting the number of samples? There is no thumb rule. If there was a thumb rule, then we could have automated the entire process. Entire process could have been automated. That is where the designer comes into the picture. There are multiple things that governs how many points, and oftentimes it is not a one shot static number of samples that you want. You probably want a dynamic or an adaptive sampling or sequential sampling kind of an approach. Okay. This is not again a runaway statement. This comes out of my research experience. Okay. Usually the meta model that we construct is only a representation. We hope that it will be as good as the original function, but we do not know the original function. We can only evaluate the original function or the response at few selected points, and if that selected point the actual function value and the evaluated function value through the surrogate is the same, then we believe that the meta model or the surrogate is a good representation. However, what we can do is we can increase our confidence in the constructed meta model by bringing in few samples. that is usually called an infill criteria, okay, or infill samples. There are different criteria that are followed to put these samples. Where do you put, how do you put? It again will talk about what your focus is, whether it is exploitation or exploration. Depending on that, you can add your samples. So, it is an infill strategy. We will discuss about few infill strategies today. What are the two things I already pointed out, right? So, one is you might want to improve the accuracy solely in the region of optima. So, let us say that you have a function like this. So, let us say that I have a representation here, and anyway this was a optimal point. That is not the exact value, there is a difference, but based on this I wanted to make sure, is this the optimal point or there are other pockets of interest. So, there are multiple ways of looking at it. One is you get a starting point and then you sample around it. So, I might want to sample around this, that is one argument. The other argument is probably your initial meta model itself was not very good. So, you might want to have other samples across and then again find out, but you cannot again randomly go and fill your gaps. So, there should be other strategies of looking at it. So, we are going to look at that. So, the first thing is improve the accuracy solely in the region of optima, which is exploitation. The other one is of course exploration. You want to enhance the accuracy of the surrogate from a global sense, not from a specific pocket sense. So, here is an example that is directly taken out of the reference book by Forrester, Alexander Forrester. So, here is a function that we are talking about, it is a polynomial function and the x bounds are between 0 and 0.5. We are taking only 3 samples here, which are denoted by the blue dots. There are 3 samples. Here is a true function denoted by the black solid line, which usually we do not have in real life, and I am constructing an RBF prediction, radial basis function. I am using a Gaussian radial basis function with 3 samples. I am constructing this is what. Now, here is your question. I can give you one more sample, but we are interested in finding the optima of this function, which you do not know. Please understand, you can just directly go do a df by dx and find the optimum, but that is not the point. The point is you do not have this function, you have the function realization at these 3 points 0, 0.25 and 5. At these 3 locations you know the function value. Based on that, for the sake of discussion, we have considered Gaussian radial basis function here, and the black line is the one that I have fitted. Now, if you can kind of in an imaginary sense erase this black line. So, the question is, if you want to find the optima of that function that does not exist and you have a choice for one more sample, where will you locate that sample? Sorry?
The left side of that 0.1.
Here?
0.1 to 2, yeah.
Why?
Because that side is very big compared to that. That is not converging to the function, original function.
No, original function and all you do not know. That is what I said, the black, you do not worry about the black, I just assume that the black line is not there.
Where the trend is changing around that region, like near the second point, either left or right.
Around the left or right, okay. Anything else?
We have discussed error metrics.
Error metrics, fine. What kind of an error metric can you use? No, that is advanced stuff. We did discuss error metric. So, there are couple of things that is given by the students. One is I could probably look for a change of trend, quite possible. Okay. The second is error metric. Press error was discussed, which is nothing but your cross validation error. There are multiple stuff. Okay. One simplistic stuff that you can think of, yes, but these are the stuff that we are going to discuss later. Okay. One simplistic thing that you can do is this: if you are looking at exploitation, you start with the starting point. What is could be your good starting point? The optima with the given function, because I do not know what the real function is. What is the best function that I have out of the 3 samples is this red function here. So, what I will do is I will run my optimization on that, and then let us say that I do not know, it could be optima here or somewhere here. Then I will put one more sample there and see how my function varies. Okay. So, let us see what happens in such a situation. So, that is what has happened here. Okay. When they ran an optimization, it probably gave up at this point, and then around that location or at that location kind of put another sample, and that is an update. And yeah, so wherever the thing is, and then you can see that there is a small difference in the graph between this and this. It is a small difference. So, you can continuously keep doing this. With the new optima here, you can put one more point, which is what we have done here. Okay. So, first the 3 blue points are the initial sample and the square red sample is an update. So, this is just one update. So, you minimize the meta model that you have built and you add a point at the optimum. Then you keep repeating these procedures. So, this was the first point, then second point, then third point, fourth point, fifth point. As you can see, this is slowly converging, or let me take back the word slowly, it is converging to your global optima. But slowly is justified because it is a one dimensional problem, that is all you are looking at. Okay. And we have already done 3 plus 5, 8 samples. So, you need 8 sample to construct a meta model. On the other hand, we also revisit, this will allow us to revisit the question, what if I started with 8 samples to begin with? Okay. Imagine that these samples were placed wide enough in a DOE setup like a LHS design or some other design. You could have got a better representation of the meta model elsewhere also, but that is your catch-22 situation. How much do I use to explore? How much do I use to exploit? This also comes from the fact of building a meta model. If you look up building meta models or surrogates from a machine learning or a classifier perspective, usually they use the terminology of design data or training data and test data or validation data. So, if I give you 100 points, there is no thumb rule again there, I am just giving an example. 70 points are used for training and 30 points are used for validation, because you want to build a model based on few samples and you want to test it at the untested or where you do not have the data already, okay, unseen. The model has not seen the data and I want to see how it predicts that point. So, again the question is, how do you balance those numbers? Should you use more for training or should you use more for testing? So, there is always an issue, and that also sometimes people suggest adaptive. That is why this one shot design of experiments like the crude LHS, there are now adaptive LHS are also there, crude LHS and all that, they all have served the community enough. Okay. But what I am saying is there are some limitations of these kind of approaches. Okay. Okay. So, after 5 iterations, this converges to the optima, you can see, and in this particular case it is a very small problem, it is a global optima in this particular case, but we cannot generalize this understanding. Okay. I am going to give you counter examples to that. Now, oh, you used a Gaussian RBF, that is the reason you got it in 5. No, that is not true. We have discussed other polynomials, we will see other meta models, we will see how it works with the different meta model. So, in this case we are looking at a second order polynomial, same set of points, it is the same example, same set of points, 3 points, and then I am fitting a second order quadratic equation. Same thing, you can go and find out your optima to be here, put another point, okay. They put a point, update point here, 2 points, okay. They constructed one in between and then again another construction, and then they found 2 updates, and then you can see interestingly it is not escaping this flat region, it will kind of get locked in that region. So, this is the exploitation issue. Instead, if you use the third order polynomial with the same 3 points, what happens is the initial curve itself looks slightly better, Of course, there are errors at these locations, but it allows, the nonlinearity allows for further exploration. Then what happens, you find the optima and then you just keep updating your samples. You can, there is a chance that you can come out of your local optima and then go here. But to begin with, how do you know that it was a third order polynomial that you want to construct? So, there is a catch in that part. Okay. And let us say I increase the number of dimensions, okay, then you cannot just shift from one order of the polynomial to another that easily. There is going to be a wide number of, I mean there is going to be a large difference in terms of the number of points or the number of samples that you need. So, these are interesting examples because these also bring out the limitations, or they kind of open up the avenues for us to explore before trying to construct any kind of a meta model. Now, we are just tweaking this problem a little bit, that is all. Okay. What we did is we just changed the bounds from 0 to 0.5 to 0 to 1, that is all we have done, and this is an interesting problem. You can see it kind of has a deep valley out here. Okay. Now, I am still using 3 points, of course, the locations are different now at 0, 0.5 and 1. Okay. And the 1 is hidden on the right side, you will see it on the right and the next plot. Same plot, I am also using a polynomial prediction and an RBF, Gaussian RBF. Okay. The red is represented by the RBF prediction and the blue is the polynomial fit. Now, our infill criteria, as per our infill criteria, what we do is this, we run an optimization on these guys and then we find out, you know, the optima is for the RBF it would have been here, for the polynomial it would have been here, and I put infill points around those locations, that is what is happening here, and I update my sample. And this is what you can see, that the RBF beautifully captures this part, but completely loses this part. We can always argue saying that if you used a different design of experiment, probably your fit was better in this region, and it, yes, even then it is a local optima. There is no guarantee that it will be your global optima. Again, in the same course I have told that our interest not always lies in a global optima. So, sometimes this might still be a good solution. Okay. So, it is left to the user and it is dependent on the application that you are talking about. The other one was about your RBF prediction, and this is a second order polynomial response surface that I use. It does not even get to your local optima in this particular case. See, please understand, I am not comparing polynomial response surface and radial basis function here. If I used some other, instead of Gaussian radial basis, if I had used some other radial basis, the effects would have been better or worse. So is the case with the polynomial. The polynomial with 3 points, the maximum you can go is only a third order polynomial. Probably with the third order polynomial, this could have looked a little better. So here it is not a 1:1 comparison, we are just presenting, depending on the meta model that you take, you might be shown a different optima. You will have to be careful about that part. So it's not even going near the local optima, which is closest to it. Okay. So that's a understanding, that's a learning from this. So this is one way of looking at it, but it's not a great way. It's as good as just filling samples, more samples. So you could rather start with a larger design of experiment and have only few samples for the exploration purpose at a later point.